Thank you very much, Janine. Thank you all for the invitation to speak at this conference. I'm joining you today from Philadelphia as one of 12 members of the research group at the architecture firm of Kieran, Timberlake. And I'll be presenting today on urban shading losses imported from Rhino 3D. So next slide, please. So as architects, we routinely negotiate a variety of forces that impact building design. These include climatic forces and human activities that impact indoor environmental comfort and energy use. But they also include regulatory and economic forces, programmatic needs, and the constraints presented by a given site and urban context. As a consequence, we rarely work with conditions that are optimal from the perspective of renewable energy generation. So the placement and orientation of PV arrays may be constrained by building and site geometry, and overshading from neighboring buildings and trees could have a significant impact on PV output, which may go unaccounted for if it's not modeled properly. I should also mention that although we've applied our urban shading calculator to a handful of projects, because of the confidential nature of much of our work, I've chosen instead to demonstrate our workflow using a hypothetical site that may be familiar to some of the folks at NREL. So what you see before you is a satellite image of Building 661 at the Philadelphia Navy Yard, which we are presently retrofitting for the energy-efficient building hub. So despite the relatively low building density of the Navy Yard, Building 661, which appears here in the center of the image with the two skylights, is bounded by 8-story buildings to the south and west, and shade trees to the east and south. Thus, if we were to consider the viability of PVs on the roof of Building 661, it would be essential to account for these shading features, as well as any potential future build-out or plantings that are defined in the master plan. Next slide, please. So as a research-based practice, we constantly move back and forth between design and analysis. And while there are certainly available software tools dedicated to analysis, we generally prefer to shortcut the process of translation between different software platforms by developing analysis plugins directly within the design software we use on a daily basis. So we commonly employ Rhinoceros 3D, or simply Rhino 3D, which you see before you, to handle our concept design and perhaps any complex geometry that occurs later in design. And the level of detail we would model out would be commensurate with a given application. So if we're studying a particular, shading device, we would naturally increase the level of resolution. But for a whole building envelope study, a fairly coarse matching model would suffice. Next slide, please. Now, one of the tools that we developed over a year ago examines the incident solar radiation on the selected analysis grid. And it maps both the spatial distribution of energy density over the selected time period, which you see in the left and lower right windows, and it also displays the cumulative power density at each time step of the simulation, which you see here in the upper right window. We initially developed this tool to build a qualitative understanding of the relationship between solar heat gain and the building envelope. So the lower right image might help us identify places where we wouldn't want to place glazing if we were in a cooling-dominated climate, while the upper right image might help us identify whether a seasonally selective shading device is providing adequate shading in the summer and adequate light penetration in the winter. Next slide, please. So with this tool on hand, it was a natural extension to consider changing the analysis grid from the entire building envelope to an array of PV panels. Next slide, please. So by sampling fewer analysis points, typically 1 point per PV cell, we could very quickly calculate incident radiation for all 8,760 hours of the year and map those distributions graphically onto the PV panels. This would allow us to refine the placement of PV panels to minimize overshading, and it would also allow us to identify areas with similar shading conditions so that we could string panels together to minimize losses due to mismatch. Of course, to calculate actual output in System Advisor module, we need to take a step back because the figures here already factor in the beam and diffuse radiation components from the Philadelphia Airport weather file, and they already factor in cosine reductions based on the angle of incidence. Next slide, please. So we modified the original tool and came up with the definition that you see here. So the image before you is a screenshot from a Rhinoceros 3D plugin known as Grasshopper. And it's essentially a graphic programming interface that any student coming out of architecture school today is quite familiar with. And in addition to allowing you to script using pre-built components, Grasshopper also allows you to build custom components through Visual Studio, as we have done for this urban shading calculator. Next slide, please. So if we zoom into the left side, you'll see that we're able to pull the analysis and context shading geometry directly from Rhino based on the layer names that we've assigned. And below that, we're also able to specify transparencies for any context geometry, which is important if we're considering shade trees, which might have partial shading. And on the right is the interface we developed for our urban shading tool that allows us to specify the date range, sample frequency, TMY file, north angle, and whether or not we want to create a modified EPW file for SAM. Next slide, please. At the heart of the tool are really two operations. First, determining the solar position at a given geographic location for each hour of the year. And second, determining whether a given analysis point is occluded from direct sunlight by any of the shading geometry. So for the first operation, we've actually employed NREL's own solar position algorithm. And for the latter, we've employed the mesh ray intersection class from the Rhino Common SDK, which is part of the Rhinoceros 3D application. Next slide, please. So first, we determine the vectors corresponding to each hour of the year. Next slide, please. Then we run a couple of nested for loops that examine each analysis point at each of the 8,760 hours of the year and test whether it is occluded by any context geometry. And we also run an analogous operation for each analysis point using a subdivided hemispherical sky dome to determine its diffuse shading coefficient. Next slide, please. So with a rather detailed model, as you can imagine, this operation, a triply nested for loop, would be rather time-consuming. So we've adapted it to run multi-threaded, and as a result, the present analysis takes about 2 seconds to run for about 200 analysis points. Next slide, please. And as I mentioned earlier, our urban shading calculator generates a modified EPW file for use in SAM with the reductions to the beam and diffuse radiation columns of the EPW file. And it also determines the tilt and azimuth based on area-weighted normal vectors of the sample grid points. Next slide, please. So to run a new simulation, one simply copies in the values into the tracking orientation interface and selects the appropriate modified weather file. Next slide, please. So as you're probably aware, SAM actually allows you to import a CSV file of beam shading coefficients, and it allows you to specify a single diffuse shading coefficient for simulation. And conceptually, there's really nothing different here in this analysis. All that we've done is simply apply these coefficients a little bit earlier directly to the weather file by reducing the diffuse radiation column, which you see here in green, by a constant factor, and reducing the beam radiation column, seen here in blue, by a variable factor for each of the 8,760 hours of the year. Sorry, those colors might appear a little bit differently on your screen. On mine, they show up as green. On yours, I think it shows up as yellow. So all this means is one less number to manually input in SAM. Otherwise, it's effectively equivalent to the beam shading input coefficients. So I should mention that in the research group, we're quite accustomed to modifying TMY files using statistical methods to reflect climate change and uncertainty due to variations in annual weather. And there's something I find quite appealing about an EPW file that describes quite precisely the microclimate of a given set of PV panels in a particular shading context. Next slide, please. So if we look at an array of PV panels without considering the shading context, we get the incident radiation profile seen here in the upper right, and the EPW file remains unchanged. Next slide, please. When we add in building context, you can see a modest reduction in the incident radiation profile and corresponding changes to the EPW file shown in the lower right. So in this figure, black means a 100% reduction in the direct radiation, meaning that all panels are in full shade. And the yellow to blue gradient corresponds to times at which some of the panels are in shade or in partial shade. Next slide, please. When we factor in the shade trees to the south, which I've represented here quite abstractly based on anticipated crown volume, you'll see a corresponding increase in partial shading at times when the sun is fairly low in the sky, but not otherwise blocked by building geometry. Next slide, please. And the effects on PV output can be quite significant, even in this relatively low urban density scenario. So this first displays an output from a typical sun power panel without any given shading context. Next slide, please. Then this next slide incorporates building geometry. Next slide. And lastly, building geometry and shade trees. Next slide, please. So these tables really summarize the results from each of the four zones of PV arrays that we showed in the original model. So without shading context, they have identical output because they're all the same angle, tilt angle, and azimuth. But considering the full shading context, some panels are reduced by as much as 19% in terms of annual output, while others are reduced by as little as 8%. Next slide, please. So if you've been paying attention, you may have noticed something I glossed over that actually has a significant impact on the way we model shade trees, and that's seasonal variation. While our present workflow requires that transparency be specified as a constant value, we know from experience that this changes significantly as leaf density changes with the seasons. We also have quantitative experience with building 661 in particular, where we've embedded temperature sensors in the exterior envelope to examine the transient thermal behavior of the existing masonry construction. So what you see in the graph is a comparison of ambient air temperature in black with exterior surface temperature of the east-facing brick wall. And you'll notice that significant spikes occur on the left side of the graph, which is March and April. And you'll notice that those spikes actually disappear come about mid-April, and this corresponds or coincides with the tree leaf density filling in as you see in the photographs. So we know that incident radiation actually is affected quite tremendously by the leaf density here. So this is something that we continue to refine in terms of our modeling practices. Next slide, please. So I mentioned we're part of a transdisciplinary research group here at Kieran Timberlake, and we comprise individuals from various disciplines: architecture, engineering, material science, sculpture, software development, environmental science, and urban ecology. And it's been really fortunate to have the opportunity to collaborate with folks like Max Piana, our urban ecologist, who appears, he's in the brown sweatshirt and blue jeans, appears twice in this photograph. And he's been conducting a literature review of leaf density modeling using hemispherical photography so that we can incorporate more robust vegetative shading models into our tool. And likewise, our material scientist, Eric Isley, who appears on the far left and just right of center, has been instrumental in applying his expertise in modeling PEVs to this present study. Next slide, please. Why do we model? Well, as I mentioned, there's a variety of forces that impinge on building design, and as architects, we really want answers to very technical questions often as we're modeling, and we try to incorporate these practices directly into modeling software. So whether it's understanding questions about natural ventilation for passive thermal strategies, whether it's actually deploying wireless sensor technology to examine transient thermal behavior, or even applying the same tools that I've presented here to correlate partial shading with tree species based on post-occupancy studies that we've done of green roofs. All of these sorts of questions necessitate bespoke modeling practices, which we carry out on a regular basis for all of our projects. With that, I think I'll conclude this presentation, hopefully a few minutes early, and would like to open up to questions.
At this time, if you would like to ask a question, it is *1 and record your name.
Hi, this is Aaron Dobos at NREL. I've got a question. So does the Rhinoceros 3D tool give you the ability to calculate the reduction in view factor at each hour of the year? That's useful perhaps for calculating reductions in diffuse radiance at each time step rather than just reductions on the beam radiance?
Yes. So essentially what we've done, and this is just as a course proof of concept, is if you saw in that earlier slide, essentially where it's calculated, used NRL's calculator to determine the solar angles. Essentially, we've done an analogous simulation where we've subdivided the hemispherical sky dome to determine the view factor to sky for any given analysis point, given its normal vector and given any given shading context. We've used that as a constant value, and we recognize that there may be some variation in terms of how that sort of diffuse factor ought to get applied depending on the sky conditions at any given time, but for now it's simply applied as a constant, which is actually consistent with System Advisor Module's own practice.
Presumably you could do the same calculation then for the view factor with respect to the ground, like for ground reflected radiance?
Yes, absolutely. So presently, actually, we are not incorporating ground reflectance, but that's certainly something that we can do with a single bounce.
This is another question from Golden. This is Nate Blair. I'm wondering, Ryan, if there's anything in the interface between Rhino 3D and SAM that you might suggest that we could improve to make it easier to collaborate between the tools?
That's a great question. Well, as I understand, there is an API for SAM, so there may be an opportunity to actually, bundle a lot of SAM's own functionality directly within Rhino. So those that have access to Rhino, which would typically be architects and engineers in the building industry, could work with that directly. In terms of actually inputting the figures, it's actually quite straightforward. I mean, just copying in the tilt and azimuth and refreshing the weather file is all that's required. Actually, my colleague Eric Isley, who I mentioned earlier, just brought to my attention having a weather file option in a parametric simulation panel would be really helpful. So if we were to run combinatorial array of about 20 different simulations, or perhaps we examined different zones or areas of PV panels and produced a whole array of weather files, or perhaps an entire array of beam shading coefficients for the full year. Being able to import those in a parametric simulation panel would be really fantastic.
Okay, great. Thank you. We'll write that down. Ryan, this is Nate again. I will add that we are, for a variety of reasons, looking at improving the ability to run multiple weather files more smoothly, as that's being requested for a couple of different use cases. So that's something that is on our radar already, but this is another use case that we weren't thinking about. So that's good.
All right, fantastic. That's great to hear.
And do we have any other questions from online?
No questions on the phone.
Okay. We did have a question from the Q&A page.
Oh, can I pull that up, or do you just repeat that to me?
It's from Crystalline.
Okay.
It says, say you had 50% of the panel shaded at a given time step, would you reduce the beam irradiance by 50%?
Excellent question. If I had 50% of the panels shaded, generally what I would do is, so essentially I cache all of the simulation results so that I can actually graph an animation in Rhino. So if I notice that I have half of the panels in shade and half of them not in shade, I'd ideally want to minimize mismatch. So I have to be cognizant of the given context. If I have them strung together so that all of the panels tied to a single inverter or are under the same shading conditions, then I would feel confident in applying that 50% reduction. Or if I had them on individual microinverters, I'd also feel confident in that. However, if I had strung together multiple panels that had very different shading conditions, ideally the visual feedback that I'm getting from Rhinoceros would clue me into the fact that I really need to consider rewiring them. Did that answer your question? Or that question? I guess
I believe that was a good answer. That question came in through the Q&A window. So again, if people who are listening want to ask questions, you're welcome to type them in the Q&A window. And then after presentations, we'll also give you an opportunity to ask questions via your phone line as well. So if there's no more questions, I think we will thank Ryan very much for his presentation.